Alright, so object-oriented programming is all about grouping data and the operations that can affect that data into a single logical unit. So in Java, just like in C++, we call this unit a class. And what we do is we provide an interface that allows someone to interact with that class. The goal is to hide or abstract the implementation details from the user of the class. So the thinking is if one doesn't need to know the underlying details, then we shouldn't burden the user of our classes with those details. Then the implementation can change and it won't affect the users of the class. So if the interface doesn't change, then none of the code that uses that class needs to change either. If the interface to a class does change, you're likely to break somebody's code who's using one of your classes. So once you finally release a piece of software and people start using it, it becomes very hard to change the interface because any change to a method name or a parameter list could break other people's software when they update to the latest and greatest. So once you release software, that's kind of a very important time where you're kind of setting your interface in stone at that point. So let's look at a few examples of interfaces that don't change. A car, for example, has a simple interface that hasn't changed really in 50 years. However, the implementation has changed dramatically over that time. Right? All of the parts, all of the components of a car are much more efficient and modern than they were 50 years ago. But because the interface hasn't changed, today I can drive a Ford, a Toyota, a BMW, a 20-year-old car, or a brand new one. Right? Because I know about the interface. That's all that I really care about as a user of a car. Implementations will change in software just like they do in automobiles. This might be because there's a new technology or a better or different hardware. Think of all the mobile devices that we're using nowadays compared to, say, 10 years ago. Or because customers just change their mind about how they want to use the application. So when a car maker designs a new fuel injection system, for example, that's more efficient, I don't need to go take a new course on how to drive the car. And this is a really good thing. So object orientation is perfect when we know that implementations are going to change. Okay. When we talk about object-oriented design, the approach is to look for things in the domain and create a class for each one. In addition, we have to specify the relationships between those things. Okay, so if we're talking about maybe modeling a car in software, well, we have these things that are important to us, right? So we have, a wheel has certain data and methods that are important. Right, so that the data might be the radius or the width of the tire and whatnot. Okay, but the wheel is not an island by itself. Of course, it might be connected to an axle. Right? And there's a relationship between the wheel and the axle. But the axle doesn't work alone either. We say, well, maybe there's a drive shaft. Right, and the drive shaft gets its power maybe from an engine. Right, and the engine is controlled by maybe a throttle. And the throttle is controlled by maybe a gas pedal. And of course, the only thing we are aware of is the gas pedal, right? We abstract as a user of a car. We don't really need to know about all these other components. Some of us know about them, but we don't have to know about them. If we can, again, we want to hide that complexity from the user. It'd be unfortunate if, in order for you to get a driver's license, you had to thoroughly explain each and every one of the parts that make up a car. It'd be unfortunate because not all of us could do it, and there wouldn't be as many cars on the road. Okay, so these relationships, they identify which objects will be calling methods on other objects. So if there's a line between two classes, what that means is these two classes can talk. Okay, or an object of one of these classes can call a method of another object. If they're not directly connected, you can't directly have have that method call behavior. Okay, and of course, what happens is the flow of control moves through the different objects in an object-oriented system. This is a little bit different than in say, a non-object-oriented C program, for example, where we still have this idea of a flow of control, but in an object-oriented system, the flow of control moves between the objects. Right, so we could think if we consider time going down this scale here, somebody, presses the gas pedal, and that sends a message to the throttle, which sends a message to the engine, which might send a little bit more power to the drive shaft object, which would be sent to the axle, and eventually it gets sent to the wheel. This flow of control moves through the objects. And one of the slightly difficult things about object-oriented programming is we have all these little objects and the flow of control moves through all of them. You really have to have this picture in your head of what are the objects and where is the flow of control as it passes through these objects. Okay, so obviously we have to identify the things in the system. Next, we think about the data and the responsibilities of each class. And eventually each responsibility is going to become a method in the class. Okay, so I think I've mentioned this before in previous classes. There's always two perspectives in object-oriented programming. You have the person or people who are implementing a class, and you have the person or people who are using the class. Now, a lot of times these two roles are the same person. We often will create a class for us to use ourselves, but that's not necessarily always like that. Sometimes we create a class and we won't be using it directly. Okay, or sometimes we're using a class and we're not the implementers of that class. That certainly happens quite a bit. In Java, we have this great Java library that we can use. Okay, so the person using the class does not really need to know any of the implementation details. They only need to know about this interface. Okay, this person only needs to know how to use it. That is, what methods of the class are going to produce the desired behavior. The implementer of the class, of course, does need to know the implementation details, but that person's not always aware of every single application the class is going to be used in. So I think of somebody created the string class, but that person could not have possibly imagined every single application that uses a string. And of course, if we go back to our car example, there's an automotive engineer that has to have great knowledge in order to design a combustion engine, right? So if there's an engineer at Ford who's designing engines, chances are they're building that engine for a car. But it turns out people use car engines in other things as well. So maybe a snowmobile or a jet ski or a 15-foot boat. The designer of that engine, I doubt, ever really imagined all the different places where that engine could be used. Okay, so all of this stuff has a name. We call this encapsulation, this idea of hiding the implementation details of a data type and only providing a well-defined interface. Now, in C++, there was an attempt made to separate the interface and the implementation. So the interface is stored in these .h files, header files, and the implementation is in the .cpp files. However, in C++, all the data details were given away in the interface, in the header file. And this was not actually a very good example of information hiding. In addition, the whole pound include mechanism is messy and complicated. In Java, there is no preprocessor, and there's no attempt to separate the interface and the implementation. Instead, all of the code is placed in a single .java file. Now, this makes reading and writing code a lot easier than the kind of painful .h and .cpp mechanism that we have in C++. The creators of Java, however, they were interested in making a clear distinction between interface and implementation. They made a clever decision to create a tool that pulls out the interface from a .java file. So if you do have to dig into the code and read it or extend it, it's nice that you can go to this one single source file. But if you just care about the interface, you could still see just the interface of the class by using the output of this tool. Okay, and the tool is called Javadoc. And I think I'll show you kind of how it works here. So here is a class. It doesn't matter what this class does. It happens to be called bitmap creator. Okay, and this is standard. This is a standard Java file. It's got imports. It's got a class. But notice it also has these special comments here. And this is special because notice it's a slash and then 2 stars right next to each other. This is called a Javadoc comment. And the Javadoc tool is going to pull out information that is in these Javadoc comments to generate a nice, friendly web page. So the Javadoc that comes before the name of a class, okay, this will show up in a certain place in the documentation. Okay, so here's the output of running Javadoc. I'll show you how to do it in a second. But here's the name of the class. Here's that description, okay, or that text that came directly from the code. So this class is used to programmatically build a bitmap image. Okay, all of that comes right from here. Notice also there's these special annotations here. So this says at author. This is identifying who the author of this class is. Okay, and that shows up somewhere in this Javadoc as well. Okay, so it's a public class, so we can put a Javadoc comment there. We'd also want to do this before, say, certain methods. Okay, public methods, because private methods and private data, they are not part of the public interface. So Javadoc doesn't do anything with Javadoc comments before private methods, only the public ones. So here's a method called addPixel. Okay, and it has takes several different parameters. Okay, so if we go to the Javadoc here and find the method called addPixels or addPixel, okay, you'll see we have this little comment, adds a pixel to the image. Right, that came right from here, and then it lists all the parameters and a little bit of information about each one. Okay, so the row, the column, okay, and whatnot. And again, the Javadoc shouldn't tell you how anything happens. We don't want to give away the implementation details. We just, in this Javadoc, explain how to use the methods in this class. So here's another one, swap bytes 16 bits. It has this return annotation. Okay, so if I go up to the top here and find this function here, it says it returns a string with the swapped bits. Again, this was pulled right out of the code. This makes creating documentation a little bit easier, because software developers, I think, generally tend to hate writing documentation, but they love writing code. So as long as we could put some of that effort into the code and have this tool pull out the interface, I think it's more likely that people actually create some documentation. Okay, so let's see how this tool works. So here, if you list the contents of this directory here, you'll see that there is the file bitmapcreator.java and this folder called docs, which if I list the contents, you'll see it's empty. So docs right now is empty. If I want to create that documentation, I issue the Javadoc command. So I say Javadoc. I give the name of the class that I want to create the Javadoc for. And if there's multiple classes in a package or something, you could say Javadoc star.java. And then there's this option -D to say, well, where do you want to put the documentation? Okay, so this says, tell me the directory where you want this documentation to go. So this says we want to create the Javadoc on this one class, and we're going to put the output in the folder called docs. Okay, so if I do this and I cd into docs and list the contents, you'll see there's a whole bunch of HTML created. Okay, and you'll see here, if there were multiple classes, all of the classes would show up here on the side if you're using frames. And then, like I said, there's nice links, right, that will take you to the different detailed method summaries and field summaries. Okay, so it's a really nice, easy tool to use. You get a lot of bang for your buck. Okay, you just write the code, and with this one command, you can generate all kinds of documentation. Of course, you have to put the effort into to write those Javadoc comments, but it's worth it. Okay, so running Javadoc, this has the effect of separating the interface from the implementation. So the implementation, of course, is the .java file. And now with this one tool, we can pull out the interface without giving away any of the implementation details. Okay, so when you want to learn how to use a class, you don't necessarily want to look at the code. Instead, you look at the Javadoc, because the Javadoc has, again, the interface and hopefully some information about how to use that interface.